Located on the banks of the Loire River, the Saint Laurent des Eaux nuclear power plant has an installed capacity of 1,000 megawatts and operates on the natural uranium gas graphite system. It has a distinctive structural feature. Its metal framework was designed to serve initially as supporting structure for heavy material handling equipment. The plant stands on an island. Its substructure consists of radial cast concrete walls built to a depth of 15 meters, reaching the limestone bedrock. These star-shaped piers are to support the reactor vessel, whose first component, manufactured on the site, is the lower tubular section, which contains all the water, steam, and instrument entry and exit tubes. On top of this tubular section, sheet metal shell rings are going to be placed in position. They are temporarily cross-braced to ensure rigidity during handling operations and concrete casting. Apertures are provided in the lower ring for the blowers and means of access. These rings, superimposed and welded to one another, will form a drum-shaped shell, making the vessel leak-proof. The reactor vessel is made of pre-stressed concrete. It contains both the reactor and the heat exchangers. The exchanger supply tubes emerge from the bottom of the vessel. Each tube is welded to the leak-proof shell by means of automatic machines. Next, the welds are carefully trimmed and ground prior to being tested by ultrasonic devices. While the concrete of the vessel is being cast, a working platform is set up within the enclosure to allow the placing of the heat insulation material. This insulation consists of thick slabs of pumice concrete. The slabs are fastened to the walls and floor of the vessel. The slabs are shielded for mechanical protection and to prevent pumice dust from being released into the primary system. The reactor vessel having reached this stage, it is possible to insert the core supporting structure. This 500-ton cylinder, consisting of cast steel segments bolted together, was assembled on the site like all the heavy components. Each section of the heat exchanger is placed inside the vessel. 30 identical sections, 10 meters high and weighing 80 tons, make up this single-tube exchanger, which is used to transfer to the water steam system the 1,700 thermal megawatts produced by the reactor. The entire assembly rests on a freely expansible framework. The supporting frame is next to be placed in position on top of the heat exchangers. It consists of a honeycomb structure made of heavy welded steel plate, 17 meters in diameter, which is to support the reactor core. The 610-ton component was fitted into the vessel with a high degree of accuracy to a tolerance of a millimeter. The cover, or top slab, is the last bulky component to be placed in position. Its tubular framework is designed to withstand the stresses of concrete casting without distortion. Cooling coils cover the surface of the leak-proof plate, leaving free the shaft openings through which the fuel elements and control rods are to be inserted. Each shaft, welded to the cover, consists of a tube surrounded by cooling coils. This component, entirely assembled on the site, is finally raised to the top of the structure. Once in position, the reactor crown is next to receive its heat insulation and then its protective cladding. As this operation is completed, the construction of the reactor core can begin. Steel posts set upright next to each other and trussed at the top by a chain form a sort of girdle inside which the stacks of graphite are to be confined. The graphite is stacked in courses of hexagonal blocks in which channels are provided to receive the fuel elements. The channels, numbering 3,300, emerge beneath the reactor crown. To guard against distortions, honeycomb plates are used to brace the channels in independent cells of 33 channels each. In order to facilitate the loading of the fuel elements, the mouth of each channel is topped by a tapered funnel. At the top of the stack are located the guiding devices for the 135 control rods. Inside these shafts, boron carbide rods suspended by cables and moved by an electric hoist hang down in some of the core channels as a means to regulate the output. Immediately below the core, samples of carbon dioxide are drawn by pipes set underneath each channel. The samples are collected by stainless steel tubes traveling in banks down to the ducts in the lower end of the vessel. Continuous analysis of gas activity will permit detection of possible breaks in the casing which would cause pollution in the system. Cladding and baffles protect the sampling tubes from carbon dioxide turbulence. As soon as the reactor is started up, this zone becomes inaccessible. The cells of the supporting apron, filled with graphite billets, form a radiation shield which, however, allows a free flow of gas. Beyond this shield, it is possible to gain access to the upper section of the exchanger in order to perform checks or repairs on the steam manifolds and on the upper part of the towers while the reactor is shut down. An access well makes it possible to go down the exchanger towers to the base of the vessel. The circulation of the heat-carrying gas from the bottom of the exchangers to the top of the stack is induced by 4 blowers. Tunnels are provided within the walls of the vessel to receive the drive shaft and the intermediate bearing. The blowers are driven by condensing turbines which receive their steam from the exchangers during normal reactor operation and form an auxiliary generator during startup or standby service. The natural uranium fuel of this system is sealed in special magnesium cans whose shape favors thermal exchanges. These cans are introduced into the graphite jackets whose main role is to withstand the stress resulting from their being piled up in the canals. In order to speed up the starting of the plant, the first 45,000 fuel slugs are being loaded manually. Introduced by bucket conveyors into the shafts going through the slab, the fuel slugs are picked up by hoists at stacking level to be inserted into the channels. An entirely automatic machine handles the fuel while the reactor is in operation. This machine has a swiveling and jointed arm 14 meters in length lowered into the reactor. This arm is a guide which forms a continuous duct between the machine and any one of the channels of a cell. Within the arm, an electrically operated grab hook seizes the jacket and slug to bring them up to a radiation-proof enclosure inside the machine. The telescopic arm may then bend back and resume its initial position. This machine is 16 meters high and weighs 630 tons. It is designed to function while the reactor is in operation and under pressure. Shields made of lead and high-density concrete enable the machine to handle and carry strongly irradiated components. It travels by means of a rail network covering the entire upper slab. After unloading a channel, the machine leaves the vessel and moves toward the fuel transfer facilities, where it will discard the irradiated slugs and pick up fresh fuel elements. A ferry bridge enables the machine to move sideways and gives it access to the disposal duct. A digital computer controls its operation. The fluids it requires are fed by a supply arm. Irradiated slugs will subsequently be removed by the deactivation pools. The fission of this fuel has released the energy converted by the 250 megawatt AC turbo generators. The first unit of Saint-Laurent des Eaux, when it went into operation in 1969, was the largest nuclear unit. It produced 1 billion kilowatt hours during the first 6 months of operation. The second unit, boosting total power of the plant to 1,000 megawatts, was connected to the network in August 1971. In creating the Saint-Laurent des Eaux power plant after the Chinon plant, Électricité de France has changed a region which was poor in energy resources into a power exporting region. This accomplishment was made possible by the continual advances achieved in nuclear engineering.